Hello world, it's Siraj, and we're going to talk about a peer-to-peer chat protocol. So you don't need to use a server, and this is what Ethereum uses. It's a protocol called Whisper, and I have a demo of it right here. So let's check it out. So my name, I'm going to put Siraj, and then I'll put the chat as hello world. I'll hit send, boom. And if I have another peer in the network, it's going to send that message to that peer. No server involved, from one peer to the other, peer-to-peer. And let me send one more message, hello again, and we send it. So in this video, we're gonna look at this app at the very end, the code programmatically. But before we get there, we've got to talk about the architecture of the Whisper protocol because it's very important to the Web 3.0 stack. So that's what we're gonna do at the end, but let's start off with talking about this stack. So recall that before I talked about the consensus layer, and the consensus layer is the Ethereum blockchain. So what it's used for is for the network to come to consensus, specifically any kind of dApp that you're building. It has to come to consensus on what are called application level constructs. These can be usernames, tweets, timestamps, anything you need the network to agree upon. That's when you would use a blockchain. So that's one part of the stack. So look at these three gray boxes here. The other two boxes, one is for Whisper, and that's the messaging stack, right? When you need your app to communicate with other apps, dApps. And then the third is Swarm, which is the storage layer, which we're going to use IPFS for, which we'll talk about later. But right now, we're going to talk about Whisper, since we talked a bit about the EVM before, and we'll talk about that more as well. But let's get right on into it. So if we look at the Ethereum stack, clearly they've had Whisper as a very crucial part of the stack. Notice that the smart contracts live on the Ethereum consensus layer. Swarm is used for file storage, and then Whisper is for dynamic communication between peers, peer-to-peer, right? So it's a communication protocol for dApps to communicate with each other. And the main feature that Whisper has that other chat protocols don't have is darkness. So what I mean by darkness is no one can trace who you are if you send a message to somebody. And even if they receive the message and it's meant for them, they have plausible deniability. What that means is no one could tell that that message was sent to them. And you might be thinking, how is that possible? If that message lives on their computer, of course it was meant for them. Well, the way Whisper is set up is such that messages are continuously routed between all peers. Whether or not that person is the recipient, they will receive the message and forward it along. And I'll talk about that in a second. It uses darkness as a feature, but it comes at a high cost, and I'll talk about that as well. So remember, this is happening off-chain. This has nothing to do with the blockchain. This is just a peer-to-peer communication protocol. And then we can think of Whisper as kind of a distributed hash table. So a hash table has key value stores. It's a data structure. A distributed hash table is the same idea, except the stores of values are distributed across a network of peers. So we can think of it that way because messages are the values that are being keyed in via the identity of the peers in a distributed way, the nodes in the Ethereum network. Or we could think of it as a datagram messaging system, peer-to-peer messaging system. You could think about it different ways, but it is a messaging system that lives in a distributed network. So this is just an example of a bunch of nodes. They're passing messages between each other. So the way Whisper works is that every message is delivered to every node. So if I'm a node in the network and I want to deliver you a message, I'm going to first send that message to my nearby peers. And what's going to happen is this message is meant for you because you have a key that can unlock that message. You and only you have that key. But regardless of whether or not it's meant for you, I'm going to send it to all these peers. Why? For darkness. Because these peers know it's not for them, but they're going to receive it anyway. And they're going to forward it to their neighbors until eventually that message reaches your intended recipient. Right? So the point of this, instead of sending it directly to the recipient, is so that it's untraceable. And once the recipient receives that message, the recipient will then forward it on anyway to other peers nearby it to completely have it be a dark protocol. Now, we can configure how dark we want it to be in that we can configure how much we want to give up in terms of speed and bandwidth and computational cost in terms of preserving that kind of identity hiding, right? So nodes are messaged to neighboring nodes, etc. And it's an identity-based messaging system. So everybody in the network has an identity. This is a unique key that's generated via the SHA-256 hashing algorithm. So at its most secure mode of operation, it can theoretically deliver 100% darkness. So there's a trade-off, though, between the level of privacy you desire and the performance. It's included by default in the Go Ethereum client, Geth, under the peer-to-peer package, P2P. And so, crucially, in order to prevent DDoSing, so if you think about this idea of how the messages are being routed, you might be wondering, wait a second, can't someone just spam the network by sending millions of messages to all the peers, and then it's just going to cause some of the peers to go offline because of the amount of bandwidth and storage it's requiring, even though it's ephemeral? Well, the way they prevent that is by using a proof of work algorithm. So messages will be processed and forwarded further only if the proof of work exceeds a certain threshold. Otherwise, they will be dropped. So all the nodes are performing a proof of work on the message. So there's a kind of computational threshold to the amount of messages you can send, and this prevents spamming the network. So what are the use cases of Whisper? So what I have here is a diagram of a decentralized game, specifically chess. And so notice that there are two players in this game. And these players are using the blockchain for the application level construct. What do the players have to agree upon? Think about it for a second. They have to agree upon the state of the game. Who's winning? Who's losing? How many pieces does each player have in the game? We can store that metadata on the blockchain, right? When it comes to the actual storage, the heavy loads of, what these objects look like and the shades and all that we can store in a distributed hash table, like for storage, right? Swarm. But when it comes to Whisper is used for them to communicate with each other, as in, okay, we see that this player is in a new state. Let's sign the new state and increment the move count and tell the other player, right? So it's kind of a message passing framework. And so dApps need to publish small amounts of non-persistent information with a preset TTL. That means time to live, right? It can be anywhere from 10 minutes to 2 days, right? If your dApp needs that, then this is a good use case, right? And if your dApp needs to communicate with another one prior to actually sending a transaction, this would be a good use case, right? So before, let's say, two nodes want to send a transaction to each other, they need to set up a deal, right? They need to settle how much they want to send to each other, when, what are the preconditions for that transaction. Whisper would be a great use case for that, right? So they can communicate before they send the transaction. If you have a dApp that provides non-real-time updates, this would be useful as well. So remember, Whisper is not in real time. There is that cost in latency and in speed to ensure darkness. And Status is an example of a messaging app. Look up Status, just Status Ethereum, that is using Whisper in production. And they raised $44 million in a few minutes using an ICO. And they're probably the most widely used app that uses Ethereum today. And it's specifically the Whisper protocol. So there have been a lot of existing solutions that Whisper has built on. For example, UDP, which is similar at an API level. They kind of took bits and pieces of these ideas from similar protocols and just used the best of them, which is generally how good research should happen. They've got BitMessage was another example, Telehash, Talks. They all had their pros and cons, but they kind of tried to synthesize the best ideas from all of them, similar to how IPFS was created. But it has some really great features. So when it comes to Whisper, the API is only exposed to contracts, never to user accounts. It's low bandwidth, so it's only designed for smaller data transfers. You shouldn't be sending giant movies on this thing, right? Just think about texts, right? Just strings of data. There's an unpredictable latency because there is a probabilistic routing mechanism here. So this adds to the darkness feature that I want to talk about, right? So because the routing isn't deterministic, meaning that we can't know who you're going to send those messages to, which order appears, there's a probabilistic aspect to it, then we can never trace back who it was or what that route was. We can't predict the route. So that's just for darkness. But because of that probabilistic nature, we cannot predict the latency, how long it's going to take to get to your recipient. And so all API calls for Whisper are contained in the web3.shh object, all of them. And we can type that into an interactive console to get a list of all functions and variables that are provided. So if we look at this code snippet here, var_f equals web3.shh.filter, and then we'll have a topic. This is a topic for the message. What is it about? It's kind of an identifier. We'll use a get function to retrieve that, and then we'll say, well, let's get the message via the topic, and then post the message via that, right? So we can get the message, we can post it via the topic. That's the parameter that we can use. Now we have these other parameters as well in terms of payload, TTL, work to prove, etc. So the payload would be the message, TTL is the time to live, how long we want it to remain active in storage, and work to prove is how much work do we want it to require to compute that proof of work. So let's get right into the architecture. And I've got this really cool image of a Solidity extension for Visual Studio just because it's awesome, but it has nothing to do with the actual architecture. But yeah, check that out. If you use Visual Studio, this is a really cool way to integrate Solidity into your IDE. Right, so let's talk about the message object. There are really two key objects here when we're talking about Whisper. We have the message, and then we have the envelope. And so, true to their name, we can store the message in the envelope, and we send that to the user. These are just objects. So each message is accompanied by a unique process of message sealing. So sealing is the proof of work algorithm, compression, which is just compressing it for faster data transfer, and encryption. And this is just for security purposes. Each message has a lifespan of up to 2 days, right? The TTL. And the proof of work it's using consists of a simple SHA-3 algorithm in which we try to find the smallest number within a given time frame. And this requires computing power to find the smallest number in a given time frame. So it kind of looks like this. So sending a Whisper message requires you to, number one, create a new Whisper message. Number two, seal it. Optionally, you can encrypt it and sign and supply with the topic of your choice. And number three is send it to your peers. So this is in Go, right? If we wanted to write this in Go, we could. But just because the client is written in Go, but we can easily write it with JavaScript. It doesn't matter if you don't know Go, just take a look at this 4-line snippet of code. So we have a topic, a message, an envelope, we seal it, and then we send it. Boom, just like that, right? Very easy, 4 steps. We could do the same if we want to listen to messages, right? So if we are a recipient, if we're intending to receive a message, we can say, well, this is the topic that we are waiting for, and now we can use the watch event listener of the Whisper object to wait for that topic to come into our network, and then we can print out what it is once we receive it. Very similar to event listeners in JavaScript. So how does this sealing work, right? So proof of work, we know that in Bitcoin, in Ethereum, in general, the consensus layer uses a proof of work algorithm using SHA-256. Well, this one uses SHA-3 to find the smallest number. What I mean by that is we have to hash the contents of the message over and over and over again into the smallest possible number that we can get it to via a proof of work. That is the proof of work. The work that is being computed by the miner, in this case, it's any node can be a miner in terms of Whisper, is how small can we make that number by repeatedly hashing it. And we can set how long we want to do that, right? That's that parameter when we send a message. How much do we want to offer the proof of work? So the cost of computing it can be regarded as the price you pay for allocated resources if you want the network to store your message for a specific time. And we can call this the best bit. The best bit is the number of leading zeros of 0 bits in the hash divided by the message size and TTL, and that is the proof of work. That just repeats over and over and over and over again. But it results in a single aggregated parameter for the message rating, or a scalar. What that means is we as developers, if we want our messages to have priority over others, then we'll need to spend more computational resources sealing them. So we can set that parameter higher if we want to have priority over others in the network, meaning faster data transfer for your message. So Whisper messages are encrypted by default. Now, the Ethereum developers encourage developers to use their own form of encryption on top of the standard encryption, but that just exists as a kind of default state. And they can be encrypted either symmetrically or asymmetrically. Remember, for symmetric encryption, they use the same key for encrypting and decrypting. For asymmetric encryption, we use different keys for encrypting and decrypting, right? Public-private key pair, similar to Bitcoin. right? So when it comes to decryption, this takes place using a private key if the message envelope was encrypted by no more than one sender. Okay, so that's it for encryption, decryption, sealing. We know the kind of routing mechanism that Whisper uses. We know that it's a part of the Ethereum stack when it comes to communication between dApps. Let's look at this example I have here about a way to send it to other peers in the network. So I've got the dApp that I just showed you in the browser. I've got Geth up and running here as well, so we can see the blockchain running. But let's look at this. So it's using Vue, V-U-E, which is a very simple framework for building web apps, right? So in our case, this would be a Web3 app. But let's take a look in this file, whisperchat.vue, which is really the main code that we want to look at. So it starts off with some HTML, headers, divs. This is our chat application. Here are some variables that we were computing before, the asymmetric public key, because we're using asymmetric encryption in this example. Here's our public key, send a message, easily hitting this button, and then it's going to send it to everybody else. Now here is the key bit here. So now we're going to look at these constant values here. So it's using a little bit of embedded Go. Don't worry if you haven't used Go before. It's a very simple language. I'm going to go through it with you right now. We're going to import some very important libraries. Web3 is Ethereum's library for communicating with its stack in general. We have two libraries for symmetric and asymmetric encryption, and then we have a hexadecimal encoding library as well. So the first thing we're going to do is we're going to say, okay, this is our data. We have some message. It's got an associated key. It's got a private key. And we're going to create a new key pair for this data specifically. And then we're going to return that data. So now we have this data object, right? So the next step for us is going to be to define this send message function call, right? So in send message, we create a message. The message has a text. It's got a name. And then it has those key parameters we talked about before, right? What's the TTL? It's by default, it's going to be 7. What's the topic? We're going to use hexadecimal for the topic, just for simplicity's sake. What's our proof of work target? Let's say 2.01. Remember, it's a scalar. How long? 100. What's the payload? And that is going to be our message, right? We're going to stringify that message, encode it to hexadecimal, and that's our payload for the message. That's what the data that we want to send in this envelope. We have another function for updating the symmetric key if necessary, and then we have a configuration function as well. But the really key function here is us saying this. We're going to say, get the filter messages, and then we're going to receive those messages as well, and then we're going to push them, right? So we can either receive those messages or we can push those messages to other peers. And when we push them, we can use the push function right here, and we can print them out here. We can set our variables, et cetera, et cetera. But yeah, it's a pretty simple protocol. All the API is available in the documentation. I'm going to have great links for you in the description as well. But definitely take a look at this protocol. I think it's very cool, and it's going to be a crucial part, whether it's Whisper or some other peer-to-peer chat protocol, of building a dApp, right? We cannot store everything in the blockchain. We cannot store anything on a server if we're building a dApp, or else it's not decentralized. And we cannot store everything in IPFS. We have to have some way for nodes to communicate in as close to real time as possible, while preserving darkness, while preserving privacy. Please subscribe for more programming videos. And for now, I've got to go dark. So thanks for watching.